As a little kid growing up in Tokyo, Houston was one of the first American cities that I had learned the name of, other than, popular cities like New York, Washington. Obviously, people learned those names, but Houston, is, well, it's not obscure, but, it's not as, globally dominant. But the reason I learned this was, of course, as a little kid, I was watching the Apollo live cast. I'm old enough. My birthday, is pretty, I've spent many birthdays already, so I was old enough to remember those telecasts. And then, they were calling out like Houston. And that was the only, and what was Houston? Well, I later learned that was the name of American city. And coming over here, I was watching, the movie on the plane was The First Man. So, so it was quite a, lots of coincidences. I'm taking a day trip to Houston and watching the First Man. Yeah. And Neil Armstrong is my hero, of course, but my biggest hero is, of course, Wernher von Braun, who wasn't at Houston, but that's, well. So, so the talk today is regarding mostly our new machine, the Post-K, and it's how we're designing it, how we're applying it, how we would be applying it, and also how it's be good for not just HPC workloads, but also for big data and AI workloads. For those of you who have known my past work, have been working on a series of machines like the Tsubame supercomputers, as the ones you see here today, and some are still in operation, and they are, some of the later versions had used, pioneered. Some people kindly say pioneered the use of GPUs in the realm of HPC. And again, these are real production machines. Most of these machines are production machines. And like Tsubame 3 is still a workhorse at Tokyo Tech, my old institution. But April 18, actually a little bit before that, I assumed the leadership of the RIKEN RCCS, which is the flagship's HPC center of Japan. And also we operate the flagship machine, the K computer. So when I became director, since we're also a research center, not just one thing we do is basically host K, but we all develop the next version post K, but also do research for future machines and future HPC. So I have a new slogan: science of computing, by computing, and for computing, because we are a center for computing. And this sort of a familiar, quoting, when you start something, you always got to quote Lincoln. So, that's something you learn to do. And then that's, I think this is a pretty, but I think this really spells out what we do, because science of computing is computer science. We study computing as scientific discipline. Science by computing is application science. We use the technologies developed here to accelerate various branches of science and engineering. And science for computing is some of the other areas, disciplines like materials and devices, photonics and neuromorphics and quantum and so forth, that will accelerate the next generation computing. Yeah. So I don't have too much time to talk about what the research we do at the center, because the focus today is on our new machine, but we'll talk a little bit about some of the research we're doing with respect to the use of the machine. So as we, maybe some of you are familiar with K computer, which is still running after 7, 8 years. And physically, I think it's still the largest machine in the world, a supercomputer, a single domain supercomputer with the largest physical size. If anybody who visits the center, it's like, it's like one of those big Google data centers, but it's a single HPC machine inside. So it has 88,000 nodes, has about 1.2 petabytes, 3 petabytes of memory. Was number one top 500, but which is less relevant these days. But in other benchmark, it still holds or have held the number one position until very recently. So it's really a workhorse. It's still, the occupancy of the machine is still like 80, 90% after all these years. But we're building a new machine, the Post-K, although it's not an official name. By the way, we have a naming contest, and we welcome submissions. And for people who get the name of the machine, of course, there'll be multiple entries. We'll draw straws, and the people who win will get this some prize. And we welcome foreign applications too. So send in your naming scheme. So I don't have to call it post-K anymore. So anyhow, but we believe that post-K is somewhat of a game changer as opposed to K, because K was a fine machine. But in terms of the biggest success of K was, technologically it was a good machine, but the biggest shortcoming of the K was that, for example, it was not commercially viable. There weren't too many systems sold other than the K itself. On the other hand, we believe post-K is the game changer for two reasons. One is it carries over the heritage, the good parts of K, the heritage of K. But as I think this was also mentioned in Laura's presentation, which I missed half of, I'm sorry, because my flight got here at 7:50, but I had to fight through Houston traffic on my Uber.
You're forgiven.
Thank you. Yeah. But we set our goal not as to build an exaflop machine per se, but our goal is to achieve 100 times speed up compared to K. Not on all the apps, but some of the applications. But we're achieving that. At least some of our apps, some of our code design, what we call the code design applications, we're going beyond 100 times speed up over the K. And, but all the K software will run. So we're inheriting the good parts of K, but also fixing the shortcomings to make it more viable, not only commercially, but to be used in other parts of the IT ecosystem. One is, for example, the processor. For the K, compared to the other processors of the competing times, the processor was okay, the chip was okay, but it was sort of mediocre, but it wasn't really better. We did a side-by-side comparison when we started the post-K project of K and other like Intel processors at the time. The performance was by and large similar. So there was no compelling reason to get the K machine because the performance doesn't change and you have a very different ecosystem. But this time it's very different in that, at least for the moment, we're seeing a lot greater performance compared to any CPUs of the day. So the performance, it's still a CPU in programming style, but in performance, it's like GPU. It excels over existing CPUs by several factors. And not just performance, but power performance. And that's really achieved by the code design we have done, extensive code design to make the processor viable for HPC workloads, but not for workloads like the web workloads, which most CPUs are designed for. And it's also very power efficient. As I'll show you the numbers later on, the power efficiency numbers match those of the latest, or in some cases exceed those of the latest GPUs like Volta, not at the CPU level. So it's a very, very power efficient. We're very cognizant of the power efficiency. And the chip also has many power-saving features. If you turn them on proactively, you can further save power. But also work with DOE to come up with power measurement standards. The old K was Spark-based, and as much as my first workstation was Spark, I have lots of affections for Spark. How many of you have used Spark stations? Yes, we love Spark, don't we? But nobody we forgot the heritage, and the Spark essentially is a goner. But so there was a big fight whether to retain Spark, but to move on to other more popular ecosystem. I was on the ARM. I was pushing ARM from the beginning, and the ARM camp won. So it's part of so it's a big ARM chip. It's part of ARM ecosystem. In fact, of the 21 or so billion ARM chips produced every year, it really sits at the pinnacle. No, we don't license in the ARM design. We just license, Fujitsu licenses just the instruction sets and also extends it with SVE. But so it's all weekend design, Fujitsu and weekend designed processor. But from an ecosystem standpoint, it's ARM. So runs Red Hat out of the box, probably runs Android. I don't know what people will do with it, but I have some rumor, I hear some rumors that runs Windows ARM version 2 as well. So, we may end up in, I don't know if it ends up in your desktop, but certainly Windows Server. And also, over the course of design, because there were lots of resurrection of AI and new emergence of new concepts like blockchain, we added new features and instructions and so forth during the design process to make it really fit for modern workloads. So it has features like low precision arithmetic that make the chip really amenable to the modern workloads like AI, and what the Japanese government calls it Society 5.0, which I think is a cool term, but we kind of copy the German Industrial 4.0, but we think Society 5 is more general. So I'll go to the details later, but just to make sure I get the points right. The POS-K ARM64 processor, on one hand, is very much a CPU. It's a 52-core processor with 13 core, what I call CMGs, core memory groups, what is called core memory groups, at 13 cores each, and has all connected by a network on chip. So this is a single chip. As you notice, it also includes a PCIe, but also the network controller. So the network is all embedded in the chip, but it's still a CPU. So like I said, all the standard stuff will run. In fact, the first chip that came back, the E0 version, just booted Red Hat right out of the box. No modifications. Right. So it's compliant to version 8.2, and not just the ISA, but complies to all the ARM standards required for a server. But it's also a GPU-like processor that has SVE 512-bit vector extension. In fact, it's double pump, just like the Skylake, although Skylake. So the arithmetically has the same capability as Skylake core, but also supports other data types like integer and 16-bit floating point. So you can have 64-way 8-bit integer vector operation, and multiply add, by the way, into 32-bit accumulation. Also has what's called the sector cache, which is this kind of unique to Fujitsu. So effectively what it does is sort of gives you a scratch pad memory or cache localization. So you can do kind of optimization you do on a GPU with a scratch pad. And this really sometimes helps in application performance. Has the best characteristics is has a high bandwidth memory on chip on package memory. So the the theoretical bandwidth of a chip is 1 terabyte per second per chip. And stream bandwidth, the measured stream bandwidth is about 840 gigabytes per second, which is about 8 times that of a Skylake. So not only has theoretical bandwidth, the chip can sustain bandwidth, and it has all the hardware features like prefetchers, of course, but also support for stream strided axes, and also memory grouping of accesses to help to sustain the memory bandwidth. And like I said, has the PCIe controller, but also has ToFuD, which is a proprietary interconnect. So if you don't want to use this, you don't have to. You can attach your favorite as HCA to the PCIe. But if you do, this ToFu has direct access to the memory. So ToFuD not only can support up to 40 gigabytes per second of injection bandwidth, it can also do things like level 2 cache injection to the other chips. So this is sort of a chip we have, we designed, and this is a chip that's almost ready to be massively produced. We already have the chip that's working and very few bugs. And the power is very low. So the co-design process went as follows. In fact, this all started back in 2009. I was part of a team of people who voluntarily started this, even before K was commissioned. So, we looked at K, said, well, this is a pretty good machine, but we really need to study the next generation because the exascale white paper came out in 2008, and we said, well, we're going to do something to really do our own part in exascale. So the effort started in 2009, and then progressed in various stages. At later stages, we had like 9 application priority areas, which were funded by the government. This is like a co-design effort center and
ECP. But so the 9 areas basically came up with 9 representative applications from the area, and these were chosen as co-design targets. And then we have various ways to basically look at this, the performances of these applications and the hardware implications of the hardware when we designed them. So initially, this was done on the FX100, which is a predecessor to the post-K chip, but had a very similar architecture, although with Spark. But we have ways to basically run this on FX100, which came out in 2014-15, and then being able to extrapolate the architecture parameters. We also, of course, Fujitsu had an internal simulator. We can also build our own internal simulator to also do this architectural exploration. Some of the co-design apps are really real apps. They're not micro, although they're mini apps. They're not they're not benchmark apps per se, but they will really represent the real workloads like this. For example, not the molecular dynamics like you see one here today in the past, but really advanced molecular dynamics that composes multiple proteomic molecules interacting within a cell, like in a membrane or in a cellular structure. So we need to, I'm sorry, this is in Japanese, but we really need to simulate, like millions of atoms at the same time over multiple proteins. This is a sub-kilometer mesh climate simulation, which was done back in 2013. So this is under a kilometer, but you need this kind of resolution in order to be able to simulate, do accurate simulation of clouds. Of course, we need the, although we can do this, we really need to speed this up by 2 orders of magnitude in order to be able to estimate the long-range climate changes. Although some people may claim that it may not exist, but we think it exists, but yeah. And also some other applications like this is a heart simulation, very accurate heart simulation done by University of Tokyo. And this not only simulates the muscular structure, but also the blood vessels and the blood flow and the electrical signals that drive the cardiovascular system. And this really lets you emulate the various medical conditions that arises in the heart, so you can do pre-diagnostic checks before you do any sorts of operations to see what the best treatment options are. So inject faults into the heart and see what the implications are. So again, you need tremendous speed up in simulations like this. So all these applications were taken and they were analyzed to fine-grained details, and ran them in a simulator and in various ways. Looked at what the SIMD width is, or to what the cache size is, cache bandwidth. And, there are lots of architectural trade-offs you have to consider. And for example, is it better to have a 1024-bit vector or 512-bit times 2 double pump vector? So you need to be able to run these architectural simulations. So in fact, when it turns out, some of the recent studies we have done, actually this was done sort of post-mortemly, and in fact with the collaboration with Intel, is this which will be in our latest publication at the IEEE IPTPS, is we've been doing some additional studies using our benchmark as well as the core benchmarks to see the implications of what the balance of the floating point units should be. So what we have done is to take the two very similar architecture CPUs. One is Knight's Landing, one is Knight's Mill. And Knight's Mill has half the FE64 capability, but we ran them in a very controlled fashion across the range of applications, which are the mini apps you saw on the post-K side, also the Coral benchmarks, to see what if these reduced capabilities in 64-bit precision would affect the application performance. Now it turns out that only 3 of the 20 or 20 plus applications, only 3 were affected only in a very minor fashion. So this really tells you that most of the applications we see, and like structural codes, or even some of the molecular dynamics code, because you're trying to do some you're trying to estimate not just the particle interactions, but you also need to do things like PME, which become more bandwidth dominant. That most of the applications are on the left-hand side of what's called the roofline curve. So with that, it really doesn't make sense to build an architecture which is specialized towards packing a whole bunch of LUs into the system. Rather, you want to spend silicon or your architectural, whatever the architectural mastery you have, onto enhancing the bandwidth of the system, mostly in memory, but also on the interconnect. And that's what and then if you can stick to standard programming models when doing that, you should do that because you have a whole ecosystem. And that's how we exactly designed the post-K chip, the x64FX chip. We have tremendous bandwidth, but in both the memory, the cache hierarchy, and also the interconnect, but we retain the standard programming model. Which is very important, and there's been, we could have also built the x86, but Intel wouldn't give us a license, unfortunately. But ARM did, although we have to pay them a lot of money. But we did, so we got the ARM license, and there's been a whole bunch of work, efforts in the industry now, and also with the centers and labs who try to enhance the ARM ecosystem. In fact, there's been lots of experiments trying to see if all the software will run on the ARM system, not any of the x86-based system software run on the ARM ecosystem. And the good news is like 99.4% of the applications ran just right out of the box. Unfortunately, they did a comparison, say, between like Broadwell's Skylake versus like Cambium Thunder X2. And if you looked at the architecture of Thunder X2, there wouldn't really be an inherent performance advantage because you have the similar memory bandwidth, and the per core performance is actually lower compared to Skylake. So the comparisons will come out to be such that they're all but then by and large the same performance. But when you take a chip like like this, which has several times more bandwidth, then of course the performance would boost tremendously. So if you want the details, there are public details available. One of which is the Hot Chips 2018 presentation. Some are also on our website that we can. It'll just give you some additional details of the chip. Like I said, this 8.2 has HBM2, 32 gigabytes of memory. Unfortunately, we don't have the DDR4 underneath like the Xeon Phi. For most applications, this should be fine because most if you have an MPI applications and they're bandwidth limited, then if they're domain decomposable and bandwidth limited, it really shouldn't matter. And I won't go into the details, but if you look at the application characteristics, that should exactly be the case. We will work on some other methods in case they're not, like when you have very random memory access or so require hashing, but I won't go into that. It's built out of 10 nanometer FinFET, about 9 million transistors, so the chip size is modest. And the peak performance of the chip, if it's anything significant, is about 3 teraflops. But it's not the most interesting metric. Probably the most interesting metric, like I said, is that we get nearly a terabyte per second of memory bandwidth. So this is a core pipeline, which is kind of hard to describe, but I will skip that. One thing to note is we have 64-bit, 32-bit, but also 16-bit have precision, and also in 16, and also we have 8-bit. And these 8-bit can do accumulation into 32-bit numbers. So although this will not help in HPC application, this will likely help in things like deep learning. But 16-bit may be usable for scientific applications if you do the proper mixed precision arithmetic, like what the Jack Dungaris group is doing. So like I said, there are 4 memory, what I call core memory groups. Each core memory group has 13 cores. 1 extra core is for the operating system. So under the Fujitsu's configuration, the users cannot touch one of the cores. But it's used to offload the operating system, because when you have a big system like PostK with more than 100,000 nodes, the operating system noise becomes crucial. But this also will be helpful in other applications too, because operating system noise always could be a killer in terms of the system degradation. Now the core is all connected now, so this is sort of like standard. But what's not standard is, firstly, all the cores are connected by crossbar, so there are no mesh or it's not all torus connection. It's all crossbar, so you get very high bandwidth between the cores. And this is connected, and the crossbar is also connected to the L2 cache, which is 8 megabytes in capacity, and also directly, and then the L2 cache is directly connected to HBM2. So there's no L3 cache. There's no level 3 cache, which is, with co-design, we judged it was not needed because, we have HBM2 has such a high bandwidth already that we didn't want to increase the latency. These CMGs are connected in the ring bus. So our recommendation when you run the MPI program is that you would have 4 MPI ranks, 1 localized to each CMG. But this network on chip is cache coherent. So if you're running applications or sharing some data within a node amongst the MPI ranks, or if you're running, it's perfectly fine to run, this as a NUMA chip. So you can have 48 threads that will access the same memory. But to optimize performance, the easiest way is to just split it into 4. This is very similar to what's done on Xeon Phi. So you get 230 gigabyte per second from L1, 115 rate, half that to L2, and 256. With these numbers, if you're an architecture person, you may appreciate these numbers. So the total bandwidth of the chip in the cache system is about 11 terabytes per second, matching the performance of 2.7 teraflops of the chip. But what about the real performance? Well, here are some kernel numbers. Like I said, the peak teraflop, peak performance double precision is about 3. I can't give you the precise number because I can't tell the final clock frequency, but it's about this. And so it's about the same as Knight's Landing. However, if you look at the DGEM efficiency, it's much higher than Knight's Landing. Knight's Landing, you get about 60% DGEM. This chip gets about 94%. Fujitsu has always been good at getting very good DGEM efficiency. And the impact efficiency as such is about 87, nearly 90%. And gigaflops per watt is about 15, which is by and large about the same as the Volta, which has about the same stream triad number, although it has a higher peak double precision flops number. For HPC workloads, probably the only application set of applications that can actually utilize this number is something like quantum chemistry codes. So most of the apps will be bound by this. So these 2 chips will likely perform very similar in these applications. So the real application numbers are being collected, and right now I don't have the liberty to disclose all this information, but just give you some of the numbers and how to think about it in the context of what's been revealed. So what Fujitsu has revealed is compared to their FX100 baseline, which is the previous machine, some of the codes like DGEM, of course you get these numbers, but things like CFD, atmospheric or seismic wave propagation, you get about 3x performance on chip-to-chip basis. But of course, this is meaningless unless you know this number, right? What this means. So one thing, I'm sorry, this is all in Japanese, but if you're an SPC expert, you know what these mean, right? MG, SB, FT, LU, you know what these are. We know what these are, right? These are universal languages. Mass parallel, right? So Fujitsu had done comparison of the FX100 compared to like Haswell, the top-end Haswell. This was a few years ago. So by doing comparison, you'll see that these chips, two systems perform by and large the same. But remember, Haswell is 2 chips per node, but this is 1 chip. So if you read these numbers on a per chip basis, this is about, so FX100 is about, on the per chip basis, about twice as fast as Haswell. If you look at the architectural numbers, that makes a lot of sense. Going back, so compared to FX100, this new chip is about 3 times faster. So compared to Haswell, on the per chip basis, maybe about 6 times faster on NAS parallel, most majority of NAS parallel benchmarks. Now, of course, you may ask, what about comparing to like Skylake or Cascade Lake? Well, I can't give you those numbers, but you can do the comparison between Haswell and Skylake or Cascade Lake and find out for yourself what these numbers mean. Probably about factor 4, but depends on the app. So I'll go a little quicker. As power management, which is compliant, by the way, with the have a whole bunch of profilers and also power management and power monitoring capabilities, which is compliant actually with a Power API that was established along with the efforts at the DOE. In fact, Livermore and other places have contributed to this. Sandia have contributed to this Power API. But I think this is the first chip that actually implements this standard. Also, the profiles of PAPI, and there's also ways for the chip not only to control voltage and frequency, but also to shut off some of the pipes when not needed. For example, for memory-bound codes, you find that a lot of these arithmetic units are not utilized, so we can shut down these compute pipes in order to save energy, and it actually does. The chip also has a mainframe-level RAS capability. So, Fujitsu has been building mainframes for the last 40, 50 years. So on the K, they have incorporated all the RAS knowledge into the chip, and they have basically done the same for this one. So, so this is a very reliable chip. Much compared to standard commodity processors, this chip is about 4 to 10 times more reliable. But that's what you need when you have a very large system that ranges to 100,000 nodes. So, the chip looks kind of like this, although has a different marking. The package is not really that big. It's about 60 millimeters square. And the chip already exists. In fact, we have the B0 version now, which is almost ready for production. This is housed in our packaging. In Fujitsu's packaging, this is packaged into 2 chips per node, which is only about this big, very small. And the reason was small, it doesn't have a DIMM. Right? So, although this is not a dual socket node, these are 2 nodes physically. And then that's packaged into this whole rack, which has 384 nodes in total. So, which is about, in double precision, about a petaflop in peak. It's about the size of a standard rack, but the maximum power consumption is about 100 kilowatts. So it's power efficient, but of course, if we make it dense, it uses a lot of power. Now, Tofu is 60 torus, although you may attach other SCAs like InfiniBand to make it a single injection port type of machine. This is already built in, so you can use this under Fujitsu's configuration. So it has 6 DMAX that's directly connected to network on chip. So it actually allows you to do cache-to-cache transfers between the chip, which is sometimes very effective to reduce the latency. So the theoretical bandwidth injection bandwidth per node is 40 gigabytes per second, which is twice the HDR speed, although it's separated into 6-dimensional links. And so 4 of the links, 2 of the links are using AOC, but the other links are using copper or internally within the board. So the latency, the physical latency is about, the shortest latency is about 0.5 microseconds, because for some of the codes are very latency sensitive. And also the theoretical bandwidth I said was about 40 gigabytes per second, but under real injection, on the real test, we get about 38, which is about 93% efficiency. on the interconnect. And the collectives are really, really fast. And overall, the 3-level hierarchical storage, including there's a NVMe per every 16 nodes. There's a cache, there's a burst buffer plus a temporary file system capability. There's a second level is Lustre. We'll have about 200 petabytes of Lustre storage. And the entire machine is about 150,000 nodes, more than 150,000 nodes in total. So that's about 7.5 to 8 million cores in total. And these are all not small cores. These are, like I said, these are all high-performance ARM cores, which is about the speed of a Haswell core. More than about 400 racks in total, a little more. The total power consumption at maximum is about 40 megawatts for the entire data center or the machine is at 40 megawatts. PUE, we're shooting for below 1.1 using high pressure, low temperature liquid cooling. But of course, it's a very large system. But compared to what the machine would have been, if we had built it out of more commodity components, if you look at the speed advantage we got by this co-designing to customize the chip for HPC workloads, rather than just to use the off-the-shelf components, is allowing us to greatly reduce the size and cost of the system. So yes, we estimate that had we taken a commodity off-the-shelf processor, the equivalent performance machine would have been 15 to 30 million, 15 to 30 million cores. So, which would have been out of our budget. So, so the software stack is there are some stuff that we have built, but looks very standard. In fact, it's very, very standard. So you got everything standard. You got C++, Fortran, Java, Python, Fortran 18, by the way, as well. You got NumPy, SciPy, MPI, OpenMP. Also trying to see if we can get other types of directive-based programming, including OpenACC and other stuff. We got all the standard math libraries and so forth. We got standard profiler, debugger. The hardware supports containers, so we're talking to Scilabs and other people to see what kind of container we'll support. Because like Dan mentioned this morning, modern software delivery is done by containers, so we should definitely exploit that. And we also have tried to work with ARM to have high-performance AI, artificial intelligence software stacks. So in essence, it's a big, it's a machine. We built our own chip, but it's an ARM chip, so it runs everything standard. It's a huge machine, but at the end of the day, it's just a huge ARM Linux cluster. It's got lots of special acceleration features, but to a user, it looked like just a gigantic Linux cluster at the end of the day. We're waiting and we're anticipating its delivery. We have a simulator out. We don't have a chip physically at Weekend yet. It's only still in the Fujitsu's factory. As much as we've been banging on Fujitsu to give us the chips. Right now, we have to give them code to run it. We get the result back. And we don't like that. But B0 production version is, like I said, is ready. It's undergoing test. And the production of the chips should start very soon. In fact, it's probably started. So, by the way, we have started the next generation machine design concept. So we always have to do these things in standard fashion. But aside from that, we'll end the existing K computer operation at the end of August. And by the end of 2019, so take about 3 months to add power, add cooling, and so forth to existing floor. So by the end of this year, the post-K installation will start. And a few months later, hopefully the pre-production operation, we can start the pre-production operation. And soon afterwards, well, a little bit afterwards, we can do the full acceptance and start the full production. late 20, probably 21, early 21. And of course, we'll move on. And we shall have, and Fujitsu and also us, we're talking to many other vendors and also like cloud providers to see if there's interest in using a chip in their own machines and ecosystem. Because again, at the end of the day, it's an ARM chip. So watch for announcements. So Fujitsu and other companies may make announcements real soon with regards to the adoption of the chip in their commercial versions and whatever the infrastructures. And the remaining time, I have 10 minutes, so I'll talk a little bit about the big data on this machine and also AI. So, in Japan, there are 3 national labs doing AI. One is AIP, which is my partner center at RIKEN. RIKEN has 15 centers. Half of these are biology, but we have some physics, but AIP, artificial intelligence, and RIKEN CCS are the 2 centers on informatics. And they're very well funded in AI, but there are other centers like ARC, which is our other national lab, which is under a different ministry, and also another lab here. Why there are 3 national centers on AI? Well, don't ask me. I didn't make the decision. Probably politics, but yeah, everybody wants a stake in the ground, right? So, and so we do have the extensive sets of big data applications on the K computer, and of course, in the post-K and other machines are growing. For example, we have an example of a big data simulation coupling the high-resolution weather and climate simulation to high-resolution radar, and doing this in real time, like 30-second interval. And we already know what's gonna be like. At least we can do this simulation now to see what's going to be like. We get a very accurate forecast of actual rainfall with 100 millimeter resolution. So this real observation, these are simulations, these are predictions 30 minutes ahead. But the one with a simulation at 100 millimeter resolution is the accurate one. The rest are useless. So we really need not just simulation capabilities in high resolution, but also assimilation capabilities. I also ran a project which is finishing, which is to investigate how the big data software, not just the software stacks, but the algorithms would port over to big machines. So one of the effort was to do the Graph 500 challenge, which was invented in 2010. And at the time, some of the people who inaugurated the benchmark predicted that the cloud may dominate top of the rankings, but it turned out it didn't, because in reality, what happened was that most of the top machines like the K and like Sequoia and those machines dominated. The reason being, and right now we've been number one in the world for 8 times. One time Sequoia beat us, but we got the crown back. No, they're doing a great job too. But all the supercomputing centers are doing a great job. But the reason is not just that we're doing a great job, but the other reason is that graph processing, big data processing, especially like graphs, is enormously network bound, memory and network bound. So in fact, even on a K computer, which has when we do the test of this Graph 500, which is a breadth first search, using 65,000 nodes or about 500,000 cores, 500,000 cores, we see that about 3/4 of the time is being used up by communication. And this is one of the fastest network in the world. Okay. So, with the injection bandwidth, it's about, on the K, it's about 15 gigabytes per second, which is about HDR speeds. So, unless your entire cloud is wired up and fully interconnected using HDR, you're not going to match this bandwidth. Right? So, if you have a gig E or even a 10 gig E, you'll be nowhere. So this spells out the need for high bandwidth interconnect, which is a differentiation from these big machines, big supercomputers, even if they're in the cloud, what these HPC machines represent versus what's in a commodity cloud. So of course, this doesn't come without the advances in the algorithm, and the fact that we got this increase in scores is through enormous efforts in trying to reduce the bandwidth. So we have the algorithms to reduce the bandwidth, and when it meets with the hardware that maximizes the bandwidth, when these two meet, then we get the maximum performance. AI, somebody I think at the panel mentioned that AI has been reborn with HPC. And in fact, it's true. I've been in the business for many years. And I don't know if anybody remembers the 1980s, the Japanese fifth generation project.
Of course.
Oh, you do? Yeah, which went nowhere, really, unfortunately. But and it was 25 years of AI winter, but came back. Now it's heaven, right? AI heaven. And partly because, we got a whole bunch of data now, but also the fact that the computing power increased by like 7 orders of magnitude. So like someone said on the panel, some of the more complicated algorithms, which were useless because they're too complicated, are now realistic. And then there are demands for even more complicated algorithms. So in fact, when you think about convergence of HPC and AI, there are two different perspectives. One is the acceleration of HPC, or how to accelerate traditional science being done by HPC using AI techniques. For example, sometimes replacing simulation. So one exemplar is to do extrapolation of your compute using empirical techniques like AI. And that's being experimented in many ways. Sometimes they're successful, sometimes they're not. But this is a very active, hot area of research. The other is to use HPC to accelerate AI. When you have to recognize lots of cat pictures, you probably need a Texas scale machine. Right? Yeah. Yes, definitely. So there's your market. Yeah. Recognizing cat pictures by the zillions. Yes. No, seriously, the AI algorithm, the deep learning algorithm is becoming increasingly sophisticated, even with the AlphaGo Plus. The amount of compute it took to train the AlphaGo, the new versions of the AlphaGo Zero, was enormous as compared to the training on the original AlphaGo. So when doing lots of work, for example, on the seismic front, we do lots of earthquake simulations, top of the class earthquake simulation, not just shaking the bedrock, but also shaking the soil, which is a soft matter. So it's very difficult to do this, but there's been some recent breakthrough at the University of Tokyo's earthquake center to deal with soft matters, and then to shake the buildings above. So the goal is to shake the entire city, which they can do now. I think this could also be useful for oil and gas. But the problem is that these soil structures are not very well known. So in order to be able to do reliable simulation, you have to generate a whole bunch of soil configurations. But now they're using AI to really reduce the number of instances of soil configuration that will match the observations in order to significantly reduce the simulation time. The other thing they did was the Gordon Bell this year, they became a finalist. And I can't tell you, they didn't win. I can't tell you why they didn't win, because I was the Gordon Bell selection chair. So, but what I can say is what they have done is to really make advances on the preconditioner selection, and in order to, again, significantly not only reduce the computation time, but significantly increase the capabilities in a way such that they were able to get like 15% 15% efficiency compared to peak on the summit, which is pretty amazing when you think of the bytes per flop ratio of the summit. Has high bandwidth, but has very high flops. To achieve that kind of a number is pretty amazing. So the other direction, we need accelerating HPC. AI using HPC. Of course, you do at the chip level, but there's a hierarchy of parallelizations you can do, and these are all independent. So actually, deep learning training is a highly parallel method. I won't go into details, but there's been a huge fight between various giants like Facebook, Berkeley, Sony, Google, Tokyo Tech, by the way, and Sony, yes, to do this image training to do this like in what they used to do like weeks on a single GPU. Now it can be done in like 2 minutes. So you can do 1 million image deep learning training in this time. Before, in fact, quicker than you cook this stuff. You cook this thing. So there's been a whole bunch of papers. We just published a paper with a new algorithm which will potentially beat Google. This will be presented at CBPR 2019. Stay tuned. Yeah. So we're doing a whole bunch of research, but with respect to post-K, we believe that it has a great potential to be a good training machine. For one thing, the processor itself is very fast with these features. Now, of course, lacks the features like tensor core, so we have to use alternative convolution kernels. But if we do that, we believe it can be, if not completely matching, but competitive to the top-end GPUs of today. Although GPUs may move ahead further, at least compared to the chips of today, it will be pretty competitive. And moreover, as doing deep learning training over multiple nodes actually require tremendous low latency and high bandwidth. It becomes an HPC problem. So, the paper I've shown here, the earlier paper, this new CBPR paper, which actually was done in collaboration with NVIDIA, is to basically come up with the ways where we can do tremendously large-scale training across thousands of processors, and then still be able to achieve convergence and speed up. So the result like this will highly be applicable to post-K. So we're targeting deep learning training to scale to 100,000, to strong scale, not weak scale, but to strong scale to 100,000 nodes. That's our goal. Oops. So we built, actually these are some of the machines I built, and hopefully we can achieve orders of magnitude increase in AI performance. So in summary, so I think we'll be, it's been 10 years of hard work by, of course not by me, not just by me, but many people involved in the project at RIKEN and Fujitsu, at various universities, our collaborators abroad, like some of the DOE labs and so forth. But it's finally coming to fruition. Like I said, memory bandwidth is the key, and also interconnect bandwidth the key. Bandwidth in the system is the key. To quote Seymour Cray, it's the bandwidth. And it's highly scalable. I think what's different from Seymour Cray's design is very power efficient because it's a modern design. So thus it's very scalable. Also, what's different is it's part of an ecosystem. It's an ARM chip. At the end, it'll be a pinnacle of all the ARM chips produced right now, at least for the moment. And it will have high performance on multitudes of applications, not just traditional HPC, but also in other areas like artificial intelligence and blockchain and others. Thank you very much.
Couple of questions.
I'm just curious why you stopped with 512-bit vectors instead of going the full length.
Pardon me?
Why did you stop with 512-bit vectors instead of like 2048?
Why did we start 512-bit vectors instead of what?
Like the SV, why didn't you make the vectors longer?
Yeah, that's a good question. So actually we did test like 1024 bits and other configurations. And by the way, this is not just 512, it's 512-bit double pumped, like the Skylake or the Xeon Phi. And all the simulation, all the co-design simulation designs we did, 512 times 2 was the better balance point in terms of performance compared to 1024. So that's why we picked 512. And we didn't start from 512 initially, with just that was done as a result of multitudes of choices we had.
A question here.
Yeah. Could you share the decision about the parallel file system? Why, among so many different choices available today, Lustre was still chosen?
Yeah, so there are several choices, as you point out. There's GFS, there's BGFS, and Lustre. Lustre primarily was chosen because Fujitsu had been working on extended version Lustre, and they put in all these reliability features and scalability features. It's a huge machine. Having said that, I don't know, I don't see any impediment in running another file system in parallel if there's a requirement. Just by, but as a first cut, we had Lustre because it had this on K. And even on K, we try to make the software stack as less proprietary as possible. So that's why we picked Lustre, which is open source. And then that was carried over.
Back there. Yep.
Yeah, Paul Emerage with HP. Did you evaluate any other processor, for example, like the NEC's Tsubasa
Yes.
with Aurora vector engine? Thank you.
Yeah, so yeah, that's a long story, but to keep it short, so Tsubasa, the SX ACE processor came out of the previous generation of SX, which was part of the K's original design. So actually, K computer you see today is only half the machine. NEC bailed out in 2008 due to financial difficulties. I'm sorry, in 2009, but that was to become part of the K design. They bailed out, they built the SX10 out of that, and then the revised version of that became the SX ACE. Now, of course, we actually have the machines in other centers. Looking at the machine, the actual performance on some of the vectorized code is good, but when you do the actual memory bandwidth assessments and so forth, actually this chip is much lower power, and we get similar performance, and it's ARM ecosystem. So I don't think there's any. No, I'm not putting down NEC, but I don't think there's any choice here.
Any other questions? Actually, I have a question for you. So a lot of the conversation here have been about talent, HPC, sort of, workforce in terms of working in the HPC space. So how does that look at the other side of the Pacific? I mean, is the pipeline of people in the HPC space, are you seeing young people wanting to get into it?
Well, that's an interesting question, because on one hand, there are a lot of people who have now become cognizant of performance. And not primarily because of HPC, but probably because of deep learning. Because it's inherently an HPC workload. So the smartest kids are now, when you ask, there have been several polls taken recently. And the good news is that, it used to be that when you ask a teenager what their aspirations are when they become, what their occupational aspirations are, and that now the number one is like become an IT person. Instead of like medical doctors or like baseball or soccer players. The number one is IT. By the way, number 6 is YouTuber. So, the reliability of this is somewhat questionable. But yeah, on the other hand, they're looking at all the IT startups and all the AI craze and all that. So it's not very clear if all of these people become hardcore systems people to the extent that they will become part of the overall HPC and high performance AI for that data analytics for that ecosystem. So, but we have some hopes. Yeah.
Okay. Any other questions? I won't finish with one question. Sure. What about RIKEN and industry? Is there a lot of collaboration, not with the IT industry, but with the more consumer industry of HPC? Is there partnerships there?
Yeah. So a lot of people regard RIKEN, because we have Nobel laureates and so forth, that we're like a basic research lab. We're like Max Planck. Yeah, and in one part we are, but before World War II, RIKEN was also the leading conglomerate of companies that spun off out of RIKEN. So one of which is a company like Ricoh. Ricoh, the copier. The Ricoh used to be a RIKEN company. And there are many other companies. When we look at the Japanese company directives, there are lots of companies named RIKEN. Some make like seaweed soup, because RIKEN was doing a study in amino acids out of seaweed extract. Somehow researchers figured out it tasted good and formed a company. And after World War II, GHQ basically decided, because RIKEN was working on nuclear physics, in order to make Japan non-nuclear, they disbanded RIKEN being a national lab. So RIKEN went private for some time, for like several years. So it became financially totally almost bankrupt, but was saved by this one woman, by the way, one woman biologist who manufactured antibiotics and sold them to pharmaceuticals to not only save lives, but make money to save RIKEN. So she's regarded one of the founding heroes of RIKEN. So, and now the RIKEN, we are spinning off our industrial liaison. So we have, my center has like 2 industrial consortiums, one with combustion and one with automotives, and we're also forming other industrial alliances. But the purpose of having the entire RIKEN spinning off this industrial liaison part to be entirely privatized. So it's a bold step, because I don't think there's any other national lab that's done this. It is basically to liaison better with the industry, because when you, from the perspective of industry, when you take oil and gas company, it's very different when you talk to a company versus when you talk to a public institution. Sometimes it's much easier to talk to a company to make deals. So that's the intention of our spinning off our entire industrial relation to be privatized, and also have things like RIKEN capital for like venture investments, but we'll see how that goes. Yeah.
Please join me in thanking Satoshi again.